we now begin to consider the issues associated with peptide synthesis. So suppose you want to make a dipeptide like phenylalanine valine. How do you do it? And this is a relevant question because short peptides are frequently needed in biomedical research labs. And there are now these biopolymer core facilities whose job it is to make peptides. So the most obvious question you might ask is, can you just take two amino acids and react them together? Okay, so a molecule of phenylalanine, a molecule of valine, will we get what we want? And the answer is no, for a number of reasons. So the first reason has to do with what these amino acids actually look like. So the mechanism that you might write for this reaction, the reaction depicted above, as drawn, would involve the NH2 of valine attacking the carbonyl group of phenylalanine in an acyl transfer reaction. Okay, so as drawn here, the first step would be the NH2 of valine being a nucleophile. It attacks the carbonyl carbon, so it's a nucleophile-electrophile reaction, and that would give you a tetrahedral intermediate. You would then need to transfer a proton. I don't have the arrows drawn for this step, but you would need to transfer a proton from the nitrogen to the OH in order to make water as a leaving group. And then the oxygen would need to come back down, the electrons from the oxygen reform the CO pi bond and kick out water as a leaving group to give the dipeptide. Okay, that mechanism might seem reasonable, except there's a problem. The problem is that amino acids, as we've already discussed, exist as Zwitter ions in solution at pH 7, which means that the nitrogen is protonated and the carboxyl oxygen is deprotonated. So what that means is, since the nitrogen is protonated, it no longer has a lone pair on it, so it's no longer nucleophilic. And then furthermore, the carbonyl group would not be particularly electrophilic because there's already a negative charge on oxygen. If you come in and attack the carbonyl carbon, putting those electrons onto oxygen, you would be putting two negative charges in close proximity to each other. And finally, there would be no way to generate a reasonable leaving group. In the mechanism that I initially postulated, we would make water as a leaving group, but that OH already had one H on it. There's not a reasonable way that we can add two more H's to it, because it's starting out, of course, having no hydrogens and a minus charge. So then, even if somehow we could get around this problem, there is also the problem of regiochemistry. So the reaction as drawn would not just give the dipeptide phenylalanine valine, it would also give valine phenylalanine through cross-coupling in the opposite direction. There is no fundamental reason why in the mechanism I drew, valine's NH2 would have to be the nucleophile. Phenylalanine's NH2 could be the nucleophile and attack the carboxylate group of valine. And then furthermore, it would also give the valine-valine dimer and the phenylalanine-phenylalanine dimer through self-coupling. There is no fundamental reason why this reaction would give just a cross-coupled product. And then furthermore, there would be no reason to even stop at a dipeptide. These dipeptides could then get attacked by another molecule of amino acid and continue to react to give tripeptides, tetrapeptides, etc. So clearly, if we're going to be able to make peptides from amino acids, we need to control this reaction. Okay, so the solution to the first problem, the problem that the amino acid exists as a Zwitter ion, and is therefore we're going to have a charged nitrogen and is unlikely to undergo nucleophilic attack, is actually to convert the OH on the carboxylic acid into a different group, which we'll call for the moment X. And what has to be true about this is it has to not have an acidic hydrogen, so we're not going to protonate the nitrogen. We'll end up with a neutral molecule and a neutral nitrogen. X has got to be a good leaving group, and X also needs to be something that can be easily synthesized from a carboxylic acid. because we want to use amino acids. They're very abundant as our starting materials. Okay, so this process of converting the OH into something else is called activating the carboxylic acid. So the first thing that might come to mind if you think back to acyl transfer reactions is, well, X can be a chloride and we could have an acid chloride, or X can be an anhydride. But the problem is synthesizing either an acid chloride or an anhydride from carboxylic acids actually requires harsh conditions that are not compatible with the amino acid functional group. You have to remember that an amino acid has at least 2 functional groups on it. It's got the carboxylic acid piece and the amine piece, and many of them have further functional groups on the side chain. So these reactions need to be done under mild conditions, and they need to be selective for what the part of the molecule, namely the carboxylic acid, that you want reacting. So the best solution that has been proposed over the years for this problem is for X to be an O-acyl isourea. Now that's something new and strange, but it'll make sense in the next slide when we go over the mechanism. And the way you get to the O-acyl isourea is you take the carboxylic acid and react it with a reagent called dicyclohexyl carbodiimide, which is shortened to be DCC. So you see that's a C doubly bonded to 2 nitrogens, similar to carbon dioxide, except because they're nitrogens and not oxygens, those nitrogens can each form another bond, and that other bond happens to be, in the most useful case, to a cyclohexyl ring. So let's look at the mechanism of a DCC coupling reaction. So the first thing you do is you actually protonate DCC from the amino acid. As drawn on the slide, the proton is coming from the carboxylic acid. Of course, if it's existing as a Zwitter ion, the proton is probably coming from the protonated nitrogen, because that's where the proton exists. In any event, we end up with a proton on one of the nitrogens of DCC. And then this looks kind of like an iminium ion, a C double bond N with the nitrogen forming 4 bonds and having a positive charge. Iminium ions are quite electrophilic, and they are electrophilic enough to be attacked by the oxygen of a carboxylate. So then you just form 1 bond from the oxygen to the carbon, break the CN pi bond, and put those electrons onto nitrogen, and that gives us the O-acyl isourea. So why did we make this complex thing? Well, the answer is this can actually become a very nice leaving group. So what will then happen is the amino group of another amino acid that's now neutral is going to act as a nucleophile. So this looks kind of like an ester. So it should make sense to you that a nitrogen can react as a nucleophile with an ester using the same acyl transfer mechanism for conversion of an ester to an amide. Okay, so you get an initial intermediate that has a positive charge on the nitrogen and a negative charge on the oxygen. We're going to need to transfer a proton off of the nitrogen, and the place that proton is actually going to go is to the nitrogen of the O-acyl isourea that is doubly bonded. This is going to make another CN pi bond with a positive charge on the nitrogen. And now when you take the electrons on the negatively charged oxygen, bring them down and kick off the leaving group, the electrons in the CO single bond that are breaking go and form a double bond from the oxygen to the next carbon. You can break the CN pi bond, put those electrons onto the nitrogen, and then you have a very stable byproduct, which is called dicyclohexyl urea. Okay, so a urea is a carbonyl group bound to 2 nitrogens. Plain old ordinary urea that you excrete when you urinate just has 2 hydrogens on each nitrogen. This is dicyclohexyl urea, and it's particularly useful because it's insoluble in solvents that are used to carry out this reaction, so it can simply be removed by filtration. Okay, so note that the O-acyl isourea cannot be isolated. Okay, the nucleophilic amine needs to be present in solution so it can attack the O-acyl isourea as soon as it's formed. So from a practical perspective, you have to have present both of the blue amino acid that is reacting with the DCC, and then you have to have the red amino acid that's doing the attacking. As we will see in the next video, this still presents a regiochemistry problem if both of them are present at the same time. So we're going to have to get around that problem, and you'll see how we do it in the next lesson.